Okay, so we're going to talk about something called doubling time and a half time. Uh, Obviously, the time it takes for something to double is called the doubling time. And the time it takes for something for halving something using decay, exponential decay, is called the halving time. Okay. We're going to start by looking at a very approximate formula here. So the approximate formula for doubling time we're going to define as the new value equals the old value times 2t divided by the doubling time. So that's all as an exponent of the number 2. Now t is going to be some sort of variable or some sort of time that they're going to give us in a problem. Okay, so let's take a look at this. Compound interest produces exponential growth because interest-bearing accounts grow by the same percentage each year. Suppose your bank has a doubling time of 13 years. By what factor does your bank increase in 50 years? Okay, so we're just going to use our little formula there and say new equals old times 2. Let's see. The formula is t divided by the doubling time. When this time the doubling time is 13, and we're trying to see what factor does our bank account grow after 50 years. So t in this case is going to represent 50. Okay, so we're looking at, going to give you an idea what we're talking about here. We're looking at by what percent would our account grow. So the new over old, if we calculate that 2 to the 50 over 13. So let me get a calculator out here. 2 raised to the 50 divided by 13, going to close that off, would be 14.38. So that would translate to 140%. So say I had $1,000 to start off with, then I could multiply that by 14.38, and I would have 14,382 when all said and done. So about 144% growth in that given time. Okay, so we're going to talk about this double time idea. And we affectionately call this the rule of 70. So for approximately growing exponential rates at some sort of percent, the doubling time, okay, so the time it takes to double something is given by 70 divided by p, which is again why we call it the rule of 70. The warning here is just be aware that this typically only works for up to about 15%. So if our growth rate exceeds 15%, then there's a more exact formula that we want to use, and we'll eventually get to see how that works. World population doubled in 40 years from 1960 to 2000. What was the average growth percentage rate during this period? Contrast this to the growth rate of 1.1% per year. Okay. So let's see. Let's going to kind of go back here. We're saying that the double time is 70 over p, or another way to write that is p is 70 divided by the double time. Okay, so if we're saying it took 40 years to double, so the percent would be 70 divided by 40. That works out to be 70 divided by 40, about 1.75. Okay. And compare that to the actual percent in 2012 as 1.1. That's not bad. That means their formula actually is pretty close to the actual. Similar to double time, we actually have something called half-life or half-time. The formula for this, again, approximation, is nu equals initial times 1/2, and I'm going to raise this to the t divided by half-time power. So that half-time is a number that they'll tell us that a certain problem that it's decaying by, it takes 50 years to get half of it. So for example, radioactive carbon-14 has a half-life of 5,700 years. It collects in organisms only while they are alive. Once they are dead, it decays. What fraction of carbon-14 still remains 1,000 years after the animal has died? Okay, so going back up to our formula here, we have nu equals initial, okay, 1/2. That 5,700 is the time it takes to get half, so that's where we're sticking that number. Okay, now in this problem they're saying what is the percent still around after 1,000 years. So if we kind of move the initial around and then replace the t with 1,000, that'll give us a percentage that represent what amount is still around. So let me pull out the calculator again, and I'm going to go with 0.5. So parentheses, actually let's do 1/2. 1/2, close parentheses, raise it to parentheses 1,000 divided by 5,700. And it gives us 88.5%. Okay, so we're still around about 88% when all said and done. Okay, suppose 100 pounds of plutonium-239 is deposited at a nuclear waste site. How much would still be present after 100,000 years? Okay, you kind of have to know that the half-life for plutonium, doesn't say this in the problem, but I will just give it to you, is about 2,400 years. Okay. So if we, let's see, let's take the 100 pounds. So nu equals 100 times 1/2, and we're going to go 100,000 divided by the 2,400 that I told you. And that's what we're trying to calculate, is about how many pounds of this stuff would still be around in 100,000 years. Alright, so let's do 1/2. Remember, you want to do parentheses for pretty much everything. Raise that to the 1, let's see, divided by the 2,400. Okay, and then times the initial 100. So I get about 5.56, or about 5.6 pounds. Pounds of this stuff is left after 100,000 years.